Leah mentioned, my name is Adam Carroll. We also have Adam Aaron over here, Mark Noakes, and Gordon is someplace right there. And we have Dominic Giuliano in the red over here. We all sort of work on robotics. And so we'll kind of cover all the bases and talk about what are robotics and things like that. Yes? Is this better? All right. All right, so you're going to hear two different terms throughout this whole presentation. The first is robotics, and the second one is remote systems. And there's a little bit of a difference between the two. The definition of robotics is a robot is a reprogrammable multifunction manipulator designed to move materials, parts, tools, and so on. And the most important part is that it is reprogrammable. It is programmable for the system. And then there's remote systems, which is the manipulation of hazardous material. And sometimes that can be with a robot, and sometimes it can be with a mechanical system. And so we'll kind of go through all of this together. So we'll start out with the history of remote systems, and we'll talk about robotics at Oak Ridge National Laboratory, and then where robots are really used. So you got Roomba and manufacturing, and then the future of robotics. So a long time ago in a galaxy far, far away, there were robots. But so obviously, you know, no one's making exactly these here today, but they are getting sort of close. But so here on Earth, where everything started was really the Manhattan Project, which is something that some of you probably have learned about in your history classes. It's World War II era, basically a buildup of a nuclear weapon device so that you know, we can defeat Germany and Japan. But sort of the start of that was there was a need for being able to keep people safe. And so you had something that was very dangerous, something that was radioactive, and you needed to be able to keep people away from that issue and that hazard. So there's two ways you can protect people from radiation, or most hazards in general. There's distance and shielding. So distance is, you know, actually just being far away from something. So if you want to envision like if you were in a room that had no lights on and there was just one light bulb over there, the closer you get to that light bulb, the more the light's going to hit you. The farther away you get from the light bulb, the less light is going to hit you. It's exactly the same with radiation. So by being farther away from the source of the hazard, the safer you are. And so to achieve this, what we have done at Oak Ridge National Laboratory is basically you develop a long reach tool. It's basically just a tool on a long pole. So you can see in this picture from probably 1940s era, you know, you have a guy and he's actually holding a pole and, you know, keeping himself away from the hazard. And then this technology is still used today because it's fairly simple. So in the other colored picture, is basically a reactor, a nuclear reactor, and it's all protected by water. And you know, they're using a long reach pole to basically move things around underneath the water. So the other way to protect is shielding. So that's putting a physical barrier between you and the source of radiation. So a lot of these can be anything from concrete, lead, steel, even water can protect you from radiation. It just depends on the type of radiation. Will tell you what kind of shielding and how much you need is best. And Dominic actually does that basically for a living, telling us how thick the wall has to be. So you can see the little guy can get close now to the source. So the problem is, now that you can be close to the source of radiation, even though you have this physical barrier in between you and the source, now what can you do? I mean, now you have this barrier. So basically they came up with with something called a through-the-wall manipulator. And so this is kind of a very old picture of the very first generation style. It basically, you could be on the other side of the wall, and through mechanical linkages and tape, metal tape, it could go over to the other side. And so as you move, it moves. And we'll show you a demonstration of that right now, assuming that this video plays. So this is a pair of through-the-wall manipulators that we have in our, basically to test out our designs to make sure that they will work well in a remote environment. And as you can see, the side that you're seeing right here, that's called the slave side, basically the manipulator side. And so that's the side that would be in the hazardous environment. And so it goes up and over to the master side. And so this is an intern that we had a few years ago, and he's actually moving it around, and it's just totally mechanical linkages. There's no technology in there, and this is basically just an advanced version of the picture that we showed before. And so he's showing that all the things that we design that has to go into a remote environment, it's very expensive to put something in and take something out, and so you want to test to make sure that it will in fact work with this sort of limited ability to manipulate it. So this is just an example of something that went into a hot cell, and we're testing it on out. And since we don't have a lot of time, I'll scoot on through it a little bit. So, as I briefly said before, a hot cell. So what is a hot cell? It's basically a little room that you have your hazardous material inside. So it could be radiation, it could be chemicals, it could be anything, but it's basically a totally contained space. And so in this example, you're using a through-the-wall manipulator like you just saw, and it goes through and into the room, and all your hazards are inside, and you're protected. But as you can imagine, they only have so much range. There's only so much distance that those through-the-wall manipulators can actually reach. And so in order to overcome that, scientists have developed what is called a power arm. So a power arm is basically, it's really simple. It's just a series of mechanical joints that are powered by a motor, and it's controlled remotely, so at a distance, by a technician. In this case, this is all very old, so it's all 1980s. So he's got a little box here, and each one of these knobs actually controls one of those joints over there on the power arm, and so that's how it's done. And you use cameras to see what you're actually doing in the hazardous environment. So these can be implemented in larger hot cells. So if you need something bigger than something that just the through-the-wall manipulators can reach, you can implement a power arm and be able to put that into a larger hot cell and have a little bit more capability. So where that technology actually went to is mostly like bombed squad robots, and you'll actually get to see one a little bit later. It's a robot called Andros, and some of you will get an opportunity to actually play with it, and it's sort of a fun thing. But that's where most of the power arms today are actually being used. They're on bomb squad robots. So if you take the power arm and you add a computer, you basically get something kind of like a robot. So back in the 1950s, Joseph Engelberger and George Duvall actually developed basically the first industrial robot. So it was basically a pick and place device, and GM went ahead and started using it in one of their lines, and that's sort of the birthplace of modern manufacturing. And so the little robot headed off to work. And so these are probably things that maybe you've seen before on the Science Channel and stuff like that. It's just basically computer controlled robots. So back at Oak Ridge National Laboratory, basically over time there became a need where you really wanted to have the dexterity and capabilities of the through-the-wall manipulator, but you wanted to have the range of the power arm, and so a servo manipulator was developed. And the servo manipulator, sort of works by having two motors, and they are supposed to position match all the time. And so the master arm over here, as it moves, so if I were to move that motor, the manipulator arm would match it perfectly in real time. And that's sort of, in a series of these motors kind of stacked up together with some tubes and some arms, will actually create your robot arm. And so I'll show you a video of that. And the niftiest part about the whole thing, and we'll show it in the video here. So once again, it's one of our interns, and so here's the master side, and here's the manipulator side over there. And so as he moves, everything just matches exactly what he does. So it's really easy. You can easily just walk up and you can immediately start playing. It's very intuitive, and it will actually provide you force feedback. So he's feeling the weight of that cone. As he's lifting his side, even though it's physically not connected to the cone, he's able to actually feel the weight of the cone, which can be helpful. It allows you to more easily be able to manipulate things because you can feel kind of the reflex force. And at some point in the video they actually show that, so we'll wait until we see it because it's pretty cool. Okay, here we go, force reflection. See, so it goes both ways. Now, in the controls, obviously you don't want to have a technician moving around something that's 45 pounds because he'd be moving it around and it would be sort of uncomfortable. But you can adjust and you can say, I want to feel 1/4 the weight, 1/10 the weight, 1/20 the weight. And then you kind of get to feel like Superman because you can lift this huge weight and it just feels kind of light as a feather. All right, so the servo manipulators are basically, it's very sort of a newer technology, and it was implemented at the spallation neutron source, which I would hope some of you have probably heard about the spallation neutron source before. I'm seeing some head nods. So this goes into their hot cell. So it's a pair of 2 arms, and they're controlled in a special control room with a series of monitors, and you know, you'll have a technician basically at a station, and he'll normally be using 1 arm at a time, but for the photo, you know, he's doing both at the same time. So outside of Oak Ridge National Laboratory, the history of robotics sort of goes back to about that post-World War II era. Here's an example. It's called a tortoise, and it's sort of the first what you could call a reactive behavior autonomous robot. It basically wobbled around, and if it hit something, it would recognize it and move away from it. And it sort of acted also like a moth. By having a light source, it tried to track where the right light source was and move towards it. So sort of the first real foray into sort of artificial intelligence. And then the next step after that was a robot they called Shaky. It was at Stanford, and this robot was really interesting because it would drive around and it had all these obstacles in its way, and it could recognize the obstacles and then go around those obstacles. And this was more deliberative artificial intelligence, where it sort of, it wasn't reacting, it was more proacting. So outside of Oak Ridge continued, there's all sorts of robots that have been invented. You have anthropomorphic, you know, like a person. You have animal-like. You have unmanned vehicles, industrial, and the future of robotics. So anthropomorphic. So there's sort of an issue with how much you want your robot to really look like a person. And it sort of has this, they call it the uncanny valley, but really it's like the creepy valley. Because you're perfectly fine looking at an industrial robot, or maybe something like this, Osmo, which Honda made. But the more it looks like an actual person, the more creepy it sort of becomes. Now, which one is the robot? It is the one on the left, but sort of a high level of creepiness. So something that people have to sort of work out. So there's also animal-like robots. So here's an example. It's a robot eel. You know, so it can travel in water, and it's pretty cool. And then there's another robot, you guys should look this up on YouTube when you have a chance. It's called Big Dog. It's a pack mule, basically, that the Army is funding. And it's pretty interesting. And then there's also robot snakes. It's just like the eel, but less water. And so unmanned vehicles, you probably have seen like the Google car that drives itself. That's basically a robot as well. And you have, the military uses UAVs all the time. And then even you can buy your own UAV, like a quad rotor would be an example of one. It can fly around and automate and follow you around. And Adam Aaron's actually working on something like that right now. It's pretty interesting. So industrial robots, so they've kind of come a long way over time. You have, you know, what you would probably say is a normal industrial robot, you know, that you would see building a car or picking and placing parts. But where the future is actually something more along the lines of maybe this. So the one on your left, this guy requires a skilled technician to program. So someone has to go through training and know a little bit about programming to be able to tell this robot what it needs to do. This one on the right here, Baxter, is basically a teach and repeat robot. It'd be more like you telling your friend how to do something. So you pick up this box and you put it over there. So you tell Baxter, pick up this box and put it over there, and then it basically repeats it over and over and over again. So almost anyone could program it, Baxter. So there's the future of robotics is going to be lower cost, easier to program, more capable, and more common. Robots more in your house, like the Roomba. I mean, that's a perfect example. Some of you probably have Roombas. That's a robot that's actually in your house and doing the chores that you should be doing. So if you're interested in this sort of future, here's a couple things that you should probably think about doing. So right now, you know, being here, that's a good step. You're learning about science and technology and being careful on steps. Do well in your math class. Take physics in high school. I know that at least in my high school, and this was more than a decade ago, but physics was an optional class. I don't know if it is today. For some of you it probably is. It's a great class. It's really going to help you out being able to go off to college and start your career in robotics. And then the last thing is join FIRST Robotics. There was icons that went along with all this. So FIRST Robotics is an excellent opportunity for you to actually sort of play with robots and find out if engineering is something for you. So you have to go to college. It's basically the way to go. You can choose a whole bunch of different mechanical engineering degrees. Most colleges don't offer a direct degree in robotics, but there's lots of degrees that can work in different areas of robotics and you can still be involved. For example, almost everyone in my group that deals with robotics, we're almost all mechanical engineers. We do have one sort of former electrical engineer, but he went off and got a PhD in mechanical engineering because it's really awesome. And then we have one nuclear engineer, that Dominic Giuliano guy, figuring out the walls. So what do you do when you go to college? So beyond just taking classes and getting a degree in engineering, you should probably look into internships. It's an excellent opportunity for you to meet companies, participate in robotics, and actually have an opportunity to meet potential employers after you graduate. All the young people in our group, including myself, basically got hired because we interned at Oak Ridge National Laboratory. In fact, I don't know a single young person that's at Oak Ridge that didn't intern there before they were hired. So if your dream is to someday work at Oak Ridge National Laboratory, that's almost certainly the best step. It allows for us to meet you, figure out if you're capable and a good fit to the group. It allows you to figure out if this is something that you would want to do as a career. So it's an excellent way to go. And if you're interested in interning at Oak Ridge, we have about 300 summer interns over the summer. Of course, my group does not take 300. That's over the whole lab. Some programs that you may want to jot down at some point would be Sully and Here and Nestles. They're all basically college level programs. So sorry, there's nothing I can really offer you at this very moment, at least in our group. But once you're in college, once you're past your freshman year, start applying for these programs. It's a great opportunity. It's definitely a good opportunity for both us and you. So you found a career, not just a job. And so the robot's stepping on the guy saying get a job. All right, any questions?
I'm curious.
And Adam Aaron would be able to help you with that. Adam Aaron, what programming languages would you want to learn if you want to program a robot?
All of them?
His answer was all of them. You have a lot of work to do.
C++ is a good start.
Did you hear that, C++? 2 pluses. Yeah, not the 1 plus. All right. Yes. All of those things. Yeah, the next generation, I mean, I only had so much time to really be able to present all the cool things that are out there, and I tried to fire through quickly so you guys can actually play with robots, but yes, there is a whole bunch of research being done about, you know, basically robotic prosthetics, and even where they've, in one case, they implanted some circuitry into a woman's brain. That she was a quadriplegic, and she can move her robotic arm entirely with her mind. It is really quite fascinating. She can go out and grab a ball and do things. And almost all of this is on YouTube. So if you just search robotic prosthetics, you're going to find a whole world out there to look at and find interesting. All right, well, since we don't have maybe any more group questions, Julia will come back on up here and she'll tell everybody how to divide up amongst the group. I'm going to be here, so if you had questions actually for me, but we're a little too shy to share it with everybody else, you can just come on up to me and I'll be happy to answer your questions as best I can, or at least refer to another engineer who can do a better job.